There is a story we have been telling ourselves for generations. A story so seductive and so cinematically satisfying that it has become almost indistinguishable from scientific fact in our collective imagination. It is the story of the starship, the gleaming vessel, the crew assembled with quiet heroism, the countdown, the leap into the dark between suns. It is the story that fills our theaters and crowds our bookshelves and whispers to us in the small hours of the night, the reassurance that the stars are not truly beyond us, that they are simply waiting, patient and luminous, for the day our engineering catches up with our ambition. I want to be honest with you today, with the same unflinching honesty that the universe itself has always offered us. That story is not science. It is not a plausible engineering challenge awaiting a sufficiently clever solution. It is not a problem that a better rocket or a more advanced fuel or a more determined civilization will one day dissolve. It is, at its core, a misreading of what the cosmos actually is, what matter actually does, and what the laws of physics have permanently inscribed into the structure of space-time itself. The truth is not that the stars are far. The truth is that the physics between here and there constitutes one of the most absolute and ferocious barriers in all of nature, a barrier not built from engineering limitations or budgetary constraints or a failure of political will, but from the bedrock mathematics of how energy, mass, and velocity relate to one another in a universe governed by Einstein's geometry. And when you sit with that truth long enough, when you genuinely absorb its implications rather than reaching for the nearest narrative escape hatch, something remarkable happens. The universe does not become smaller or less wondrous. It becomes almost unbearably more so. Imagine for a moment that you have commissioned the construction of a sail, not just any sail. You have gathered the finest artisans in human history, people whose hands can coax gossamer threads of silk into geometries of breathtaking precision. The weave is perfected at the level of individual fibers. Every knot is a masterpiece. Every panel catches wind with an efficiency that approaches the theoretical maximum. You launch this sail into a sandstorm, not an ordinary sandstorm of sand and grit, but a storm composed entirely of microscopic shards of diamond, each one moving at hypersonic velocity, each one carrying the kinetic authority of a particle accelerator in miniature. It does not matter in that scenario how perfect your weave is. It does not matter that you have studied the geometry of sailing for centuries. The shards do not negotiate. They do not acknowledge your craftsmanship. They will find every fiber. They will detach every thread from every other thread. They will turn your magnificent sail into a dispersed cloud of meaningless fragments, moving in slightly different directions. The silk never had a chance, not because the weavers failed, but because the fundamental mechanics of the encounter made failure the only possible outcome. Now, I want you to hold that image very carefully, because the interstellar medium and the velocities required to cross it are precisely that sandstorm. And the most sophisticated spacecraft our civilization has ever imagined is precisely that silk. This is not metaphor deployed for dramatic effect. This is physics, drawn directly from what we know about how matter and energy interact when relative velocities climb toward the cosmic speed limit. Let us begin with energy itself, and the first of the three profound physical truths that govern this question. Special relativity, Einstein's extraordinary geometrical reordering of how space and time relate to one another, contains a consequence so counterintuitive and so merciless that it took the scientific community years to fully absorb its implications. When an object accelerates, it gains kinetic energy. That is familiar. What is not familiar, what Newton never imagined and classical intuition cannot prepare you for, is that as the velocity of an object approaches the speed of light, its relativistic mass, the mass that resists further acceleration, does not simply increase. It scales toward infinity. Mathematically, you can write this down in a single compact equation, and that equation will tell you something that no amount of wishful thinking can revise. As you push your spacecraft closer and closer to the speed of light, the energy required to achieve each additional incremental fraction of that speed grows without bound. There is no asymptote you coast past. There is no breakthrough velocity beyond which the math relents. The energy demand simply keeps climbing, and climbing and climbing until the universe demands of you something that is not physically possible to supply. Consider a spacecraft of genuinely modest proportions, not the city-sized vessels of popular science fiction, but something closer to a probe, something in the range of a few thousand kilograms, the kind of mass that an ambitious engineering program might actually be able to construct and launch. To accelerate that probe to even 10% of the speed of light, which would still require roughly 40 years of travel time to reach even our nearest stellar neighbor, the energy required is on the order of 10 to the power of 19 joules. That number needs some context. The total energy consumption of our entire global civilization, every power plant, every engine, every electric light on every street in every city on Earth, running continuously for an entire year, amounts to roughly 6 times 10 to the power of 20 joules. We would need to dedicate a significant fraction of our planetary energy production for a full year simply to push a modest probe to a tenth of the speed of light. And that calculation has not yet accounted for deceleration, has not yet accounted for life support, has not yet accounted for any of the systems that an actual crewed mission would require. Push the velocity higher to the 50% or 80% of light speed that the journey mathematics actually demands if you want to arrive within a human lifetime, and the energy requirements do not double or triple. They accelerate exponentially into a regime that exceeds what our sun radiates in years, decades, centuries. The geometry of space-time is not simply indifferent to our ambitions, it is structured in a way that makes those ambitions physically incoherent at the energies they require. The padlock is not on a door that a better key might open. The padlock is woven into the mathematical fabric of what energy and mass and velocity mean in this universe. But suppose, for a moment, that we wave away the energy problem. Suppose we imagine a civilization so advanced that energy is abundant beyond anything we can currently envision. There is a second truth waiting for such a civilization, one that does not yield to energy, abundance, or engineering sophistication, because it is rooted not in what we can do, but in what the interstellar environment itself does to anything moving through it. Space is not empty. This is one of the most consequential misunderstandings embedded in our popular conception of the cosmos, and it is a misunderstanding that the mathematics of high-velocity travel punishes with catastrophic severity. The interstellar medium, the material that fills the space between stars, contains on average roughly 1 hydrogen atom per cubic centimeter. At the scale of ordinary human experience, that is almost nothing. The best vacuum we can produce in a laboratory on Earth is denser than that. But the interstellar medium also contains microscopic dust grains, molecules of various kinds, charged particles carried on stellar winds, stray cosmic rays arriving from distant astrophysical catastrophes. At the velocities we have been discussing, these components of the interstellar medium cease to be negligible background noise. They become a weapon of almost unimaginable destructive efficiency. When you accelerate a spacecraft to 10% of the speed of light, a hydrogen atom that the ship encounters in its path is not simply a hydrogen atom anymore. From the reference frame of the ship, that atom is an incoming projectile carrying the kinetic energy of a particle that has been accelerated to relativistic velocities. A single such encounter releases energy on the scale of what we see in particle physics accelerators. And in the interstellar medium, you are not encountering one hydrogen atom. You are encountering billions of them every second, distributed across the entire cross-sectional area of your spacecraft's forward surface. The cumulative energy deposition is staggering. But even that is not the most dangerous aspect of the encounter. A dust grain, a particle perhaps 1/100th of a millimeter across, colliding with a spacecraft moving at a substantial fraction of the speed of light, delivers an energy equivalent to a small explosive detonation precisely focused on a microscopic impact point. The physical consequence of that impact is not a dent or a crack in the conventional engineering sense. It is a cascade of nuclear spallation reactions in which the nuclei of the spacecraft's hull material are fragmented by the collision into a spray of secondary particles, each carrying their own destructive energy deeper into the material. The hull does not simply wear away, it is actively transformed at the nuclear level into a radioactive cocktail of broken atomic fragments. The material that was once a carefully engineered alloy becomes progressively and irreversibly a source of lethal radiation that the crew must somehow survive, even as it is simultaneously failing to protect them from the next impact. There is no material known to physics, and no material that theoretical considerations suggest is possible that could survive this bombardment across interstellar distances. The shielding problem is not a matter of finding a sufficiently thick or hard substance. It is a matter of the fact that at these velocities, thickness itself becomes paradoxical. A thicker shield means more mass, which means more energy required to accelerate it, which means more exotic fuel required, which means more mass, in the recursive loop that the rocket equation makes so brutally, mathematically clear. And a thicker shield still does not fully solve the spallation problem, because the secondary particles produced by nuclear spallation travel forward through the shielding material, depositing their energy in the interior of the vessel regardless of how much material you pile in front of them. The vacuum of space, at the velocities that interstellar travel demands, is not a peaceful highway stretching between the stars. It is an active particle accelerator aimed directly at the face of your spacecraft, running continuously, without interruption, for the entire duration of the journey. Now we arrive at the third truth, and it operates on a time scale that dwarfs the dramatic immediacy of the first two. It is the truth written into the second law of thermodynamics, and it concerns not just a spacecraft, but any complex, organized system attempting to maintain itself across the extraordinary duration of deep interstellar transit. The second law of thermodynamics is perhaps the most quietly ruthless principle in all of physics. It tells us that the total entropy of a closed system, the measure of its internal disorder, can only increase or remain constant over time. It can never spontaneously decrease. Order does not maintain itself. Organization does not persist without a continuous investment of energy from outside the system. Every machine ever built, every organism ever evolved, every circuit ever designed exists in a continuous, losing battle against the statistical tendency of matter to drift toward its most probable configuration, which is always a configuration of higher disorder than the one we started with. A spacecraft crossing interstellar space is, by the very nature of the journey, a closed or nearly closed system. The energy available to it, whether from onboard fuel or from ambient radiation, is finite and diminishing. The journey to our nearest stellar neighbor, at even an optimistic velocity, would require something between 40 and several hundred years, depending on the velocity achievable. For any crewed mission, this means decades of biological metabolism, mechanical operation, electronic computation, structural stress cycling from thermal expansion and contraction, and the continuous degradation of every material that constitutes the vessel. Consider metals alone. The cyclic thermal stress experienced by a spacecraft as it moves through regions of slightly varying radiation environment, combined with the bombardment of cosmic rays we have already described, causes fatigue fractures to propagate through metallic structures at rates that ground-based engineering can measure and model with considerable precision. The timescales of interstellar transit exceed by many orders of magnitude the designed operational lifetimes of even our most robust engineered systems. A spacecraft designed to last 50 years of continuous operation, which would already represent an extraordinary engineering achievement, is still a spacecraft that will spend the next several centuries, at minimum, continuing its journey after that designed lifetime has expired. Biological systems are even less forgiving in this regard. The human body is an extraordinarily sophisticated thermodynamic engine, one that evolution has refined over billions of years to operate within very specific parameters of temperature, radiation, nutrition, and gravity. Remove those parameters, and the system begins to fail. Low gravity causes bone density loss, cardiovascular deconditioning, and fluid redistribution in ways that become cumulatively debilitating over years. Cosmic radiation, in the quantities experienced outside the protective envelope of a planetary magnetosphere, causes DNA damage at rates that overwhelm the body's repair mechanisms, elevating cancer risk and accelerating cellular aging. These are not speculative concerns. They are effects that have been measured in astronauts on the International Space Station over periods of months, effects that worsen nonlinearly as exposure duration extends. No known biological intervention, no hibernation technology, no genetic modification that current science can envision resolves the fundamental thermodynamic problem of maintaining ordered biological complexity across the timescales of interstellar transit. The physics does not bend for clever solutions. The second law does not issue exceptions. Entropy accumulates, complexity decays, and across the centuries, the grand interstellar voyage becomes something that no amount of initial investment in engineering or biology can prevent from becoming a cold, silent drift of disorder through the dark. There is something I want to sit with for a moment, something that I think the relentless focus on engineering solutions and propulsion schemes causes us to overlook. The three physical truths we have walked through today, the relativistic mass barrier, the lethal particle environment, the thermodynamic inevitability of decay, are not independent problems awaiting independent solutions. They are interconnected expressions of a single underlying reality, the reality that the universe has a structure, and that structure contains within it certain absolute boundaries that are not subject to renegotiation. These are not walls that a sufficiently advanced civilization will one day dismantle. They are more fundamental than that. They are the walls within which the game of physics is played for every civilization in every epoch around every star. There is a phrase that sometimes appears in discussions of advanced extraterrestrial intelligence, the idea that a civilization sufficiently more advanced than ours would appear to us as if performing magic. And there is a sense in which this is true, particularly with respect to information processing, energy generation, and material science. But even magic in this sense is constrained by what the mathematics of reality permits. A civilization a billion years more advanced than ours cannot travel faster than light, cannot absorb infinite energy, cannot maintain perfect thermodynamic order in a closed system. The laws we have been discussing are not the laws of our current level of ignorance. They are the laws of the universe itself, tested across every scale and every regime accessible to our instruments, holding with a precision that no experimental anomaly has ever successfully challenged. What this means, and I think this is genuinely one of the most profound consequences of taking physics seriously, is that the silence of the cosmos is not mysterious. It is expected. It is, in a deep sense, the natural outcome of a universe in which the laws we have been discussing apply universally. Every civilization that has ever arisen around any star in this galaxy, and likely in this universe, has confronted the same three truths we have been examining. The relativistic mass barrier has faced them. The particle accelerator of the interstellar medium has faced them. The second law of thermodynamics has faced them. And those laws have said, with the same impassive mathematical certainty they say it to us, you are here, and the distances are what they are, and the physics is what it is. There is no defiance of this. There is no workaround that centuries of additional development will eventually produce. The interstellar distances between civilizations are not a temporary inconvenience in the story of intelligence in the cosmos. They are a permanent feature of the physical architecture of the universe, as permanent as the speed of light itself, which is, of course, precisely what they are ultimately constructed from. I want to be honest about what this does to me, personally, as a physicist and as a human being who grew up watching the same films and reading the same books that you did. There is a grief in it, a real, genuine grief at the closing of a possibility that felt for a long time like a promise. The stars are not coming for us. We are not going to them. The cosmic neighborhood is not a neighborhood in any sense that a civilization bound by our laws can actually explore. And sitting with that truth, without flinching, without reaching for the comfort of speculation about technologies that violate what we know, requires a particular kind of intellectual courage. But here is what I have found, after sitting with it long enough. The grief transforms into something else. Something that I find more valuable than the comfort the old story offered, because the old story was, in the end, a way of not quite looking at the universe directly. It was a screen between us and the raw, unmediated truth of what and where we are. And when you remove that screen, when you let the actual physics land on you with full force, what you find on the other side is not desolation. What you find is a quality of attention, a sharpness of presence, a recognition of what is actually here, that the fantasy of departure was quietly draining away from us. This world, this particular planet, this precise location in the cosmos where physics has permitted the emergence of beings capable of measuring and contemplating physics, is not a waiting room. It is not a launching pad that we have not yet perfected. It is the thing itself. The oceans and the magnetic field that shields us from the radiation we now know would destroy us without it. The atmospheric chemistry that maintains the temperature envelope within which carbon chemistry can organize itself into living systems. The gravitational well that keeps our water from dispersing into space. These are not background features of a story whose real action happens somewhere else. They are the story. They are the specific, contingent, extraordinarily improbable arrangement of physical circumstances that made everything we are and everything we have ever thought possible. The mathematics that tells us we cannot reach the stars is the same mathematics that explains with breathtaking precision why the stars are where they are, why they burn as they do, why their light carries the spectral signatures that tell us their composition from 25 trillion miles away. It is the same mathematics that describes the hydrogen atom, the electromagnetic interaction, the nuclear force that makes stellar fusion possible and therefore makes starlight possible, and therefore makes photosynthesis possible, and therefore makes us possible. The uncompromising nature of that mathematics, its absolute refusal to make exceptions for our wishes, is not its failure, it is its most magnificent quality. To understand the physical laws that permanently constrain our reach is to understand them precisely enough to appreciate the extraordinary precision with which they have conspired in this particular corner of space-time to produce a world that can understand them. That is not a consolation prize, that is the prize. The hard, uncompromising, beautiful final prize of taking physics seriously enough to let it mean what it actually means.